Hi, and welcome back to my channel. So, in my previous video, I showed how how is it possible to use a low-pass filter to clean up the output of the HRF, okay? With the idea of sending this output to potentially an amplifier for long-distance communications, for example, in the ham band, in the bands of a ham radio. Uh, so I use this filter that I made by myself, following the circuitry described in this website, as I mentioned already. So now I've been thinking a little bit. Okay, so this filter actually manages to reject, to remove some unwanted frequencies, so the high frequencies from my signal. But how does it dissipates these frequencies? So where do they go basically? And so I started thinking, and I realized that I was not understanding properly what was happening. And the fact that since all the components in this filter, are either inductors or capacitors, there is no resistor that can dissipate any energy in terms of heat. So the fact that the reality is that all the rejected frequencies are being reflected. They are not disappearing, but they are going back to the source. So to the HRF in this specific case. So I wanted to, so this was for me an opportunity to try to understand the situation a bit more. Unfortunately, I bought some time ago this thing that allows precisely this type of measurement. So it's called a directional coupler. So I don't know, from mini circuit. So I don't know if you can the focus works well enough, but this device functions as follows. It has an input port, this one. It has an output port, this one. So the signal just goes from an input to the output straight, basically. So it's just there is a direct connection between input and output. But there is a third port. And this third port takes a little portion of the energy from the input to the output, so of the signal, and push it out here, okay? Attenuated by minus 20 dB. So for example, if here I have a signal of 0 dB, the signal is going through to the output, and here I'm getting a minus 20 dB copy of the input signal, okay? So the idea of this type of thing, devices, is to get a sample, or yeah, a small portion of the input, to look at it, and then leave it do its job on the output, basically unchanged. But we're just taking a little part of it in this coupled port. Okay, so I just want to use this to measure the reflection of my filter here. So first of all, let's see how this device works in practice thanks to the spectrum analyzer. So by the way, this thing has a specification from 0.2 megahertz to 250 megahertz. So I'm going now to set up the spectrum analyzer accordingly here. So I'm going to set a starting frequency of 0.2 megahertz, so 200 kilohertz, and a stop frequency of 250 megahertz. Okay, perfect. Next, I'm going to connect the tracking generator, which is this cable here, to the input of the coupler. Right. So let me connect it quickly. Okay. And the output port of the sampler is going to the output port of the directional coupler. So I'm making the connection. Rather, so this is stupid. So I want to connect the spectrum analyzer to the couple port. Okay, and then I'm going to connect a dummy load to the output port of the directional coupler. So let me explain what's going on here. So my tracking generator is going to emit a signal from 0.2 megahertz to 250 megahertz in this direction. The main part of the signal is going to this dummy load, so theoretically is being consumed completely here without any reflection, theoretically. and here we should get just the signal from the tracking generator reduced by 20 dB. So in theory, this is the behavior of the directional coupler. So let's see if this is the case. So I'm going to set up the tracking generator. So I'm setting up the tracking generator to emit, so let me actually change the amplitude. So the reference here is 0 dB. So at the top here now we have the first line is 0 dB and it's 10 dB per division. So here I have a line that I'm going for the moment to turn off, okay? So again, let's go back to the tracking generator. It's going to output at minus 10 dB. So we're getting a signal here at with energy minus 10 dB. And so we are expecting to get out here something at minus 30 dB. So let's see if this is the case. And this is the case, okay? So this is precisely the response that we're expecting. So this device works just fine. Okay, so I'm turning off the tracking generator at the moment. Okay, so now the trick to measure reflections of filters is quite simple. So we're going to disconnect things here. We are just inverting output and input. So now the input is going to be the output port, okay? So the tracking generator is going to the output of the directional coupler. Okay. Right. In the input, we put the dummy load. Let's connect it. And as usual, to the couple port, so the minus 20 dB port, we plug the input of the spectrum analyzer. Okay, so what is the idea here? The tracking generator will send a signal at minus 10 dB in this direction. Okay, so since this is the direction out from output to input, this signal will not be sampled here. Okay, so this only takes only samples signals in this direction. So in fact, part of the signal sent by the tracking generator to this dummy load potentially will be reflected, because this is not a perfect dummy load. It's in fact a cheap dummy load from AliExpress, probably 50 cents of euros. Okay, so some part of the signal might be reflected back, and this reflection will be captured by this couple port and reduced by 20 dB. So let's see how it works. I'm going to activate the tracking generator again using minus 10 dB of power, and let's see what happens. Okay, so as you can see, we get this figure here, and so the figure starts here. We get a minus 67 dB energy, you see. So this is what we get here at this port. So we know that this is something attenuated 20 dB. So in reality, we have something at around minus 46 dB being reflected from the dummy load back to the tracking generator. Okay, so since the tracking generator is emitting at 10 dB, here we have a reflection at around, we said 47 dBs, so it's 37 dB down. Okay, so 37 dB down is like less than 0.1% of energy is being reflected at this frequency. But as you can see, as we increase the frequency and we move towards the 250 megahertz, this reflection increases. Okay, this is because the dummy load is not perfect. So when the frequency increases, it becomes less and less a perfect dummy load. So it starts reflecting, which is not a desired behavior, but still is not reflecting very much here. So we get 53 dB, which we know it in reality, since this is a minus 20 dB couple, means 33 dB. And so we are 23 dB below the tracking generation signal. So the signal which is being reflected now is less than 1% of the original signal. So Remember, minus 20 dB means 1%. Okay, so this is the reflection caused by just the dummy load. So let's see now the reflection caused by my filter. So I'm going to stop the tracking the generator. Okay, stop. So I'm going to replace now this dummy load with my filter, which has an input port, and then here I already attached a dummy load. So the idea is that the filter will filter out some frequencies, then reach a dummy load where theoretically, well, every frequency should be absorbed, but we already just saw that in fact even this dummy load reflects back something, okay? So let's see how this works in practice, thanks to the spectrum analyzer. Okay, and so let me activate the tracking generator again at minus 10 dB, and let's see what's going on. So again we get the expected behavior. So after about from 50 megahertz and something, so for the large part of the spectrum here from 200 kilohertz to 250 megahertz, we see that the signal is being completely reflected, okay, because we get minus 30 dB minus 30 dB line here. So this in reality means minus 10 dB, and that's exactly the full power emitted by the tracking generator, okay? So let me just focus on the part of interest, which goes from basically up to, let's say, 20 megahertz. Okay, so this is the response that we have. So it's kind of interesting, you see. The reflection depends on the frequency. So we have these bottoms here. So at 6 megahertz, we have very, very little reflection, and similarly at 14 megahertz. But already at, let's say, if we use it at around, let's say, the 10 megahertz. Remember, this is a 10 megahertz low pass filter. Here we get a minus 38 dB. So this is a minus 18 dB in reality. Again, this is a minus 20 coupling. And so, since the tracking generator is outputting minus 10 dB, it means that, well, the reflection is minus 8 dB compared to the input, okay? So it's more than 10% of the power being reflected back. So it's just, I mean, I find this fascinating. I hope I managed to explain things properly. For sure I did not manage, but now I understand what is the meaning of this curve here. You see the red curve that you get in this website that I suggested for designing these circuits is precisely this response in terms of reflections. So it's kind of expected to have curves of this type. The curve I get is slightly different for some reason, but still it has this type of behavior. So anyway, the consideration related to the ACRF here that we experiment with in my previous video is that, okay, the ACRF is very fragile, okay? So for example, never try to transmit with the ACRF without an antenna, because there will be a 100% reflection. But also never try, I would say, to transmit, for example, at 1 gigahertz signal when you have a low pass filter of 10 megahertz, okay? Because that 1 gigahertz is going to be completely reflected. So the filter will act basically as an open circuit. So will reflect completely that wave, and that can damage the ACRF. So just be careful when you do this type of things with the ACRF, that, you know, filters made of capacitor and inductors, in fact, reflects the unwanted signals. They do not just let it disappear as I was imagining before. Yeah, just one last consideration. Always remember that my nickname is the RF noob. So really, basically, I'm just learning these things right now. So I'm doing these videos just to have fun and, you know, to follow my learning process and document my experiments. But yeah, of course, there are so many things that I don't know, and this was one of them. Hi, I thought to add this little part of the video. So in fact, I found this filter, this 30 megahertz low pass filter on eBay a couple of months ago. It was very inexpensive, so I decided to buy it, even if at the moment I don't have any radio for. I'm not even a licensed operator. But I thought it was a nice, interesting thing to also analyze this filter, since we are talking about this, using the exact same setup. So the signal is going to the filter, and then is being terminated with a dummy load, and we are measuring the reflection attenuated by 20 dB. So this is the setup. So as you can see, the spectrum analyzer is going to is set from 200 kilohertz to 250 megahertz. So I'm going now to activate the tracking generator, and let's see what is the response. So on the majority of the spectrum, actually just after 30 megahertz, so here we are at 37, the signal is being completely reflected. So it's at minus 30 dB in the spectrum analyzer, which actually in reality, since this is a 20 dB attenuation, means minus 10 dB, which is exactly the output sent out by the tracking generator. So 100% of the signal is being reflected. So let's focus on the part of interest. So frequency, stop frequency, 38 megahertz. And so we get a behavior that is not as evident as in the filter that I made by myself. Probably this is a higher quality. But still, yeah, the reflection is going up with frequency, then going down a little bit, and going up again, then finally up a lot. So in a sense, I don't know, the response looks a bit different. Internally, the construction is exactly the same. So this is made of just capacitor and inductors. It's very big because these capacitor and inductors are very big. They can sustain a lot of power. This is rated for 1 kilowatt, while this is probably not even rated for 10 watts, or 5. This is really for low signals. So, but the design is exactly the same, but the curve that you see as a response here, it's in a way much nicer. I don't know if it is much nicer. It's just a slightly different. It's more flattened. It does not have the big curves like the ones appearing out of this filter. So yeah, and to conclude this video, in fact, I would like to mention that I've started in my channel to add a list of channels that I like very much. In particular, this channel I think is amazing. So it's the channel of W2AEW, which is his ham radio identifier. And so in this video there is just an amazing source of information. So if you want to learn, like I'm doing, about RF, I think this is by far the best source on YouTube, and probably on the web as well, in terms of simple lectures, not too difficult but not really a leader. So this is just a fantastic resource if you're interested on this topic. So thank you again, bye.